class, welcome to week 2. This week we will be doing chapter 3, Electromagnetic and Particulate Radiation. It is the radiographer's role to be familiar with the different types of radiation to which patients are going to be exposed to and to be able to answer questions and educate patients when they ask you. I've had patients ask me, how much radiation am I receiving with this chest x-ray? Am I getting more than I would if I laid outside in the sun? Or how about if I went to a tanning booth or a tanning bed? So I get questions like that all the time. So it's good for you to be educated about that and how to answer your patients when they ask something like that. The radiographer should consider him or herself as a resource for the public and should be able to dispel any myths or misconceptions about medical imaging in general. Both ends of the electromagnetic spectrum are used in medical imaging. Radio waves are used in conjunction with the magnetic field in MRI, magnetic resonance imaging, to create images of the body. And then X-rays and gamma rays are used for imaging in radiology, nuclear medicine. One difference between the ends of the spectrum is that only high energy radiation, which is your X-rays and gamma rays, have the ability to ionize matter. More specifically, the radiographer should always be able to explain to a patient the nature of the ionizing radiation, as well as any risks and benefits, and should be an advocate for the patient when you're discussing this with other professionals. The radiographer should also understand the nature of radiation well enough to safely use it for medical imaging purposes. And with this in mind, the electromagnetic spectrum is discussed first, followed by a discussion of the particulate radiation. So we'll be looking at the electromagnetic radiation, and then after that, we'll dive into the particulate. In the latter half of the 19th century, we had a physicist by the name of James Maxwell, and he developed his electromagnetic theory, significantly advancing the world of physics. And in this theory, he explained that all electromagnetic radiation is very similar in that it has no mass and it carries energy in waves as electric and magnetic disturbances in space. And it travels at the speed of light. His work is considered by many to be one of the greatest advances of physics. Electromagnetic radiation may be defined as an electric and magnetic disturbance traveling through space at the speed of light. You can see in this image here, it's showing electromagnetic radiation, that is energy traveling at the speed of light in waves as an electric and magnetic disturbance in space. The electromagnetic spectrum is a way of ordering or grouping the different electromagnetic radiations. All of the members of the electromagnetic spectrum have the same velocity, which is the speed of light, or 3 times 10 to the 8th meters per second, which also equates to 186,282 miles per second. They only vary in their energy, wavelength, and frequency. The members of the electromagnetic spectrum from lowest energy to highest are radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. The wavelengths of the electromagnetic spectrum range from 10 to the 6th to 10 to the negative 16 meters, and the frequencies range from 10 to the 2nd to 10 to the 24th hertz. The members with the highest energy and the shortest wavelength are the most ionizing. So the members to the right on the electromagnetic spectrum, which would be to the right of the visible light, are going to be your more ionizing. And then the members to the left of visible light are less or non-ionizing. The ranges of energy, frequency, and wavelength of the electromagnetic spectrum are continuous. That means one constituent blends into the next. Shown here is the electromagnetic spectrum, and you can see the electromagnetic spectrum energy, the frequency, and the wavelength. The ranges are continuous with energies from 10 to the negative 12 to 10 to the 10th. And the energy is shown in EV, and frequency is shown in hertz. But you can see to the right of the visible light, you have your ultraviolet, you have your X-rays, and your gamma rays. And to the right would be more ionizing because it's higher energy and shorter wavelength. The wavelength is going to be shown in frequency, which is hertz. And then to the left of the visible light, we have the infrared, we have the microwaves, the radio waves, and that's going to be all your low to no ionizing over there because it's low energy and long wavelengths. Electromagnetic radiation is a form of energy that originates from the atom. Electromagnetic radiations are emitted when changes in atoms occur, such as when electrons are going to undergo orbital transitions or atomic nuclei emit excess energy to regain that stability. Unlike mechanical energy, which requires an object or matter to act through, electromagnetic energy can exist apart from matter and can travel through a vacuum. With electromagnetic radiation, it is the energy itself that is vibrating as a combination of electric and magnetic fields, and it is made of pure energy. Energy and frequency of electromagnetic radiation are related mathematically. The energy of electromagnetic radiation can be calculated by the following formula: E equals HF. And in this formula, E is the energy, H is Planck's constant, which is equal to 4.135 times 10 to the negative 15 eV per second, and 6.626 times 10 to the negative 34 joules per second. And then F is the frequency of the photon. So E equals HF is energy equals Planck's constant times the frequency of the photon. The physicist Max Planck first described the direct proportionality between energy and frequency. As frequency increases, so does energy. So those are directly proportional. Planck theorized that electromagnetic radiation can only exist as packets of energy, and we call those photons. The constant H, which is named for Planck, is the mathematical value used to calculate photon energies based on frequency. The energy of the electromagnetic spectrum ranges, again, from 10 to the negative 12 to 10 to the 10th electron volts, or EV. Electromagnetic radiation exhibits properties of a wave or a particle depending on its energy and in some cases its environment. The phenomenon is called the wave-particle duality. This is essentially the idea that there are two equally correct ways to describe electromagnetic radiation. We can talk about electromagnetic radiation based on its wave characteristics of velocity, amplitude, wavelength, and frequency. The velocity for all electromagnetic radiation is the same. It's the speed of light. The amplitude refers to the maximum height of the wave, and the wavelength is a measure of the distance from the peak of one wave to the peak of the next wave. Frequency refers to the number of waves that pass a given point per second. And in this image here, you can see the electromagnetic wave measures. You can see that the electromagnetic wave is described by its wavelength, which is the distance from one peak to the next. You can see the amplitude, which is the maximum height of a wave, and you can see the frequency, which is the number of waves that pass a given point per second. Because all electromagnetic radiation travels at the same velocity, the relationship between wavelength and frequency is inverse. That is, the longer the wavelength, the lower the frequency, and vice versa. So wavelength is generally expressed in meters. And because we are dealing with very large to very small wavelengths in the electromagnetic spectrum, the actual measure is typically in exponential form. For example, like 10 to the negative 11 meters. Frequency is generally expressed in hertz, and 1 hertz is defined as 1 cycle per second. Long wave AM radio waves have frequencies from 500 to 1600 kilohertz, or 0.5 to 1.6 megahertz. 1 kilohertz is 1,000 cycles per second. 1 megahertz is 1 million cycles per second. Shorter FM radio waves have frequencies in the hundreds of megahertz. And then, as with electromagnetic radiation wavelengths, frequencies are also very large or very small and are expressed in exponential form as well. Electromagnetic radiation with very short wavelengths, such as X-rays, have frequencies measured in million trillions of hertz. For example, 10 to the 19th hertz. The basic formula for calculating the wavelength or frequency is velocity equals frequency times wavelength. This formula is simplified when applied to electromagnetic radiation because the velocity of the spectrum is the same for all. So that's the easy part. We have the same velocity, so we don't have to worry about that portion of the formula. So we replace V with C, and that is the constant symbol for the speed of light. And our formula becomes C equals frequency times wavelength. When solving for frequency, this formula becomes F equals the constant divided by wavelength. And this is simply a mathematical rearrangement to isolate the unknown value. When solving for wavelength, the formula becomes wavelength equals constant divided by frequency. And again, it's just to isolate the unknown value. Electromagnetic radiation can also be characterized by how it interacts with matter. When we discuss it this way, electromagnetic radiation may exhibit more characteristics of particles depending on its energy. An individual particle or photon of electromagnetic radiation has an energy given by the Planck formula. Higher energy photons, for example, X-rays and gamma rays, are going to act more like particles, whereas lower energy radiation, the radio waves, microwaves, are going to act more like waves. So the intensity of the electromagnetic radiation is going to diminish over distance. This should be a familiar observation with sources of light or perhaps a campfire. This is an application of the inverse square law. The intensity of the electromagnetic radiation diminishes by a factor of the square of the distance from the source. This concept is illustrated with a light source in the figure on the slide here, and it is very important to medical imaging. And then you can see here, the closer you are to the light, the more intense. The further away you are from the light, the less intense. So just like it was talking about a campfire, right? So if we are cold, then we walk closer to the campfire, right? And then the heat is intense, it's extremely intense. So as you get closer to the source of the fire, or in this case with X-rays, the source of the X-ray photons, the intensity is going to be way more than if you were, let's say, 6 feet away. Okay, so the further away you get, the less intense the fire is, and the less intense the X-ray beam is. And that's why they tell us with portable X-ray to make sure and stand at least 6 feet away from the source of the electrons and the source of the X-ray photons, the primary beam. We want to make sure that we are further away, because as X-rays travel through air, they lose energy and then they just kind of fizzle out. So before they reach us at the 6 foot mark, they're going to be gone. They'll be totally fizzled out, and we won't get any of the radiation scatter. X-rays and gamma rays have characteristics of both waves and particles. Because of their high energy, they exhibit more particulate characteristics than those at the other end of the electromagnetic spectrum. They do exhibit the wave characteristics of transmission, but they can also burn the skin, and their intensity varies according to the inverse square law, both of which are particulate characteristics. One additional particulate characteristic that is unique to the highest two members of the electromagnetic spectrum, which are the X-rays and the gamma rays, is their ability to ionize matter. When a photon possesses this sufficient energy, it can remove electrons from the orbit of atoms during interactions. And this removal of an electron from an atom is called ionization. The atom and the electron that was removed from it are called an ion pair. Ionization is the characteristic of X-rays and gamma rays that make them dangerous in general and harmful to the patients if misused. When tissue atoms are ionized, they can damage molecules and DNA and cause chemical changes in cells by mutating the DNA. There are differences between X-rays and gamma rays, and that comes from each one of them originates from a different energy source. Gamma rays originate in the nuclei of atoms and represent the excess energy the atom is giving off to reach the stable state. X-rays originate through interactions between electrons and atoms. X-rays are produced when fast-moving electrons within the X-ray tube strike the atoms of the metal in the target, which is the anode. The low end of the energy spectrum begins with radio waves. One common use of radio waves is in magnetic resonance imaging, MRI. The basic principle of operation of MRI hinges on the fact that the nuclei of hydrogen atoms are magnetic. So when placed in a strong magnetic field, the nuclei will absorb and re-emit radio waves of a particular frequency. Through this processing of these emitted radio waves, images are constructed. Because human tissue contains large amounts of hydrogen, which are seen usually in the molecules of water and fat, a substantial signal is observed. And it is important to note that radio waves do not ionize atoms. And so therefore, this makes MRI non-ionizing. Microwaves are used routinely to transmit cell phone signals and heat food. Microwave towers can be seen across the landscape, and microwaves generally provide a reliable signal. In microwave ovens, a microwave generator is used to create microwaves, electromagnetic waves at a frequency of about 2500 megahertz, and those are directed towards the food. Microwaves hit the atoms of the food, giving them excess energy, and this energy causes a vibration of the atoms and molecules. The atoms then release this excess energy as heat, which increases the temperature of the food to the point of cooking or warming it. So microwave ovens work because microwaves are readily absorbed by waters, sugars, fats, but not by glass or plastic. Metals reflect microwaves and prevent them from being absorbed by the food and could damage the generator, which is why metals cannot be used in microwave ovens. Microwaves can cause heating of tissues, but they do not ionize atoms. So microwaves are also non-ionizing. Infrared light is a low-energy electromagnetic radiation just above microwaves on the spectrum. It is sometimes used to beam information between electronic devices. For example, the signal sent from the television remote to change channels or to change the volume or any kind of settings on the television is infrared light. It may also be used to send information between portable electronic devices like cell phones, computers, or between personal computers, digital assistants, what are they called? iPads, things like that. And again, infrared light does not ionize atoms, so it is non-ionizing. So when they're saying that, people are getting brain tumors from cell phones, that's highly unlikely because the energy coming from the cell phones are non-ionizing. Visible light is likely the most familiar member of the electromagnetic spectrum. It represents the colors visible to the human eye. White light consists of all of the colors of the visible spectrum together, and then an object that is perceived as white is reflecting all of the wavelengths of light at once. When we see a color, the object is absorbing all of the wavelengths of light except the one we see. The color black represents absorption of all of the color wavelengths. The visible spectrum is a tiny portion of the electromagnetic spectrum, and again, visible light does not ionize atoms, so it is non-ionizing. Ultraviolet light has energies approaching those of X-rays and gamma rays. So UV light emitting bulbs are used in tanning beds because it is that part of the sunlight that causes the darkening of the skin or burning if the exposure is excessive. UV light can be harmful, and routine exposure has been demonstrated to cause skin cancer, like melanoma. UV light stimulates melanin production in the skin cells, and it causes the darkening of the skin or the damage to the melanocytes. This results in the cancer or melanoma, but it does not ionize the atoms. All of these are members of the electromagnetic spectrum, but each behaves differently depending on its energy. And none has the ability to ionize matter except for X-rays and gamma rays. Like X-rays and gamma rays, alpha and beta particles have the energy to ionize matter. Particulate radiation is more often dealt with in nuclear medicine or radiation therapy. And imaging professionals must understand this type of radiation to be able to be an advocate for patients and the public. To understand particulate radiation, you must first understand radioactivity. And radioactivity is a general term for the process by which an atom with excess energy in its nucleus emits particles and energy to regain stability. This process is called radioactive decay. Elements that are composed of atoms with unstable nuclei are said to be radioactive. Some radioactive elements, such as radium and uranium, exist in nature, whereas others, such as technetium, are artificially produced for various purposes. Technetium is produced for nuclear medicine studies. A radioactive substance does not suddenly decay all at once. Decay is a process that may last minutes or billions of years. So one term used to describe the rate at which a radioactive substance decays is called half-life. And a half-life is the length of time it takes for half the remaining atoms in a quantity of a particular radioactive element to decay. The half-life of radium is 226. For example, that's 1,620 years. half the unstable atoms are left after that time, and half of that amount, or 1/4, is left after another 1,620 years, and so on. Half-lives are used to measure radioactivity because that is how radioactive substances happen to decay. We know that the unit of measure for radioactive decay is the Curie, or becquerel. The electromagnetic photons emitted in this process, which are the gamma rays, have already been discussed previously, and we know that they are the alpha and beta particles. An alpha particle is actually 2 protons bound to 2 neutrons. It's basically the same makeup of the nucleus of a helium atom. Alpha particles have a net positive charge, 2 protons giving a charge of +2. For example, uranium-238 is naturally radioactive. Each uranium atom has 92 protons and 146 neutrons. When it decays and emits an alpha particle, uranium then has 90 protons and 144 neutrons and becomes an atom of the element thorium. Alpha particles do not travel very far because they are relatively large and cannot penetrate most objects. Even in passing through air, they quickly pick up electrons that are attracted to their net positive charge and become helium atoms. A helium atom has 2 protons, 2 neutrons, and 2 electrons. When an alpha particle picks up the 2 electrons, it then becomes a neutral helium atom. So in this picture here, you can see it's an alpha particle, and an alpha particle is composed of the 2 protons, 2 neutrons, and the same makeup of the nucleus of a helium atom. A beta particle is an electron that is emitted from an unstable nucleus. It does not originate in an electron shell. A beta particle is much lighter and smaller than an alpha particle and can penetrate light materials. Betas have a much larger range and may ionize many atoms along their path. And shown here is a beta particle, which is an electron that is emitted from an unstable nucleus, and it does not originate from one of the electron shells. It comes straight from the nucleus. Beta particles may have a positive or negative charge. The negatively charged beta particle differs from an electron only in that it is originated in the nucleus of the atom and electrons are in the orbital shell. The positively charged beta particle is called a positron, and when beta particles are stopped by collisions with other atoms, they join the atoms just as the electrons do.